So let's review 15 years, but this is kind of in the context, it was unintended. But this year we're all talking about the, giving tribute to the life of Gordon Moore. And as a consequence, talking a lot about Moore's Law, right? And in the Moore's Law's context, 15 years is nothing. But I think one of the things that I heard yesterday in a session is we started with one transistor in 1958, and then it was two transistors in 1959, and it kept doubling every year for a while, and then every 2 years for a while, right? So it eventually gets to be a lot of grains of rice, and it's a huge number of transistors now. You know, I was actually born in 1958 in December, so in March I was one cell, right? In 1959, though, I was a lot more than two cells, right? But my growth was like this, and the semiconductor growth is like this, you know? These curves, you know, these shapes of curves are kind of important. Only 15 years ago is when eBeam initiative started. In 2009, we had already gotten to the point where it was 193i. That was kind of a done deal, right? Source mask optimization, SMO, was already being done, but not programmable yet, right? So it was like almost there. Alternating PSM, attenuating PSM, all these techniques, RET techniques, they were already being done. OPC was already being exercised, but not really quite to the same extent as now, right? So this was an era where also just worldwide Lehman shock, right? So it was like, not a comfortable time, but that's when we started. And what we talked about was how eBeam is central no matter what the alternative lithographies were chosen, whether it's EUV or optical or immersion or maskless lithography, which is also, of course, using eBeam to directly write the wafer, or nanoimprint or DSA, which really affects any of them. eBeam is central to all of the things that we do, either in making the masks or making the masters or writing the wafers themselves. What we started the eBeam initiative talking about was to the subject that we were just on, character projection, right? Something that Hans Pfeiffer, rest his soul, he invented while he was at IBM in 1979 or something. We had this thought that maybe character projection, cell projection can be used to do things. And that's how that was the initial motivation for forming the eBeam initiative. And of course, we just heard from Matthias talking about where that has gotten this tech to, right? You can write any shape, right? Look, these are curvilinear shapes written completely accurately with basically the VSP technology, right? So it's not limited to Manhattan shapes, diagonal shapes, curvilinear shapes, bow ties. 2009, when we started, Vistec made a presentation, and they were talking about eBeam direct write in that way too. And by the way, the Vistec technology can be used to write masks or wafers, right? So that's an interesting thing too. And oh yeah, one thing that I didn't show. So Advantest also presented. And in the case of Advantest, this is one of those things where the D2S logo is different now. Working together with Fujitsu and a subsidiary of Fujitsu called eShuttle, there was actually a business using character projection to project standard cells in just one character, right? And being able to project that. And the thought back then was once that's established, you can make the standard cell shapes anything you want, it doesn't have to be Manhattan, right? It could be like any curvilinear shape, any diagonals. DRAM diagonals can be done that way too, and that was the thought. But because this was a transition time in 2008, 2009, when the Japanese semiconductor industry was basically exiting the business, right? So this idea never came to be a production idea, but it was an interesting beginning to the set of thoughts. And so the eBeam initiative started that way, talking about these specific kinds of ideas. But we also talked about alternatives, right? Like directed self-assembly, or Hayashi-san talked about nano imprint and using eBeam to do the templates, and specifically using multi-beam to do that at the time. And all of those things were coming about because of EUV being delayed. EUV was beginning to be worked even in the 1990s, right? But it was much delayed, and it got to the point at one point. These are the percent of respondents indicating EUV will never be used in high volume manufacturing, right? So one of the things that eBeam initiative started to take on was to do these luminary surveys that Jan mentioned. Every year we ask a set of questions to the luminaries under the theory that asking luminaries is meaningful. It's an opinion survey, not a fact survey, right? But it's meaningful because luminaries know things under NDA. They can't say what they are, what they know, but what they know affects their opinion. So their opinions are valuable in that way. And of course, the other way is luminaries are making decisions about what to invest in the future, whether it's their people or equipment or materials or anything, right? So what luminaries know is important to track. And so the collective whole of approximately 70 to 80 luminaries, asking them specific questions is a meaningful thing. And what we found really pretty dramatic, right? Decrease in confidence in EUV over 2012 to 2014, and then a sudden increase in confidence, right? From 2014 to 2015. So that was interesting, and that's what was going on that gave rise to the need for thinking about, well, okay, if EUV is not going to come, 193i is only going to last for a little bit, RAT technologies are only going to last, go so far. What else can we do, right? So that was the context of where we were back in those days. So one of the things that we talked about while we were doing that was also eBeam direct write, but not doing character projection, instead using multi-beam, right? Actually, Hans Loschner, I don't know if he's here or not, but he asked me to give an invited talk at one of these sessions, and I remember that this was one of the slides that I did in that talk, and I remember him teaching me about how to give an invited talk, because I never done it before. So I really appreciate that. I learned a lot in that process, and I still use it today. But what this slide talks about, this picture is Keilei Tenko's Rebel, but IMS, Keilei Tenko Rebel, Mapper, and Multibeam were principally the 4 companies that were doing multi-beam based wafer direct write at the time. And that was a great set of attempts. And one of the things last year, it turned into a multi-beam presentation by David Lam of, the Lam of Lam Research, who talked about how the chip ID, or customizing each die, is an useful application for eBeam direct write, right? But in both of these cases, both the BizTech case and Advantest case, multi-beam case, it never got to the point where it was fast enough to be a production tool for wafer writing, and besides, EUV worked, right? So the need for that went away. In the meanwhile, between 2011, 2010, and 2012, I think in 2011, IMS did an incredibly wise thing, right? They did the SWOT analysis in business, right? And they said, you know, what's the strength of eBeam? The strength of eBeam is precision and accuracy. What's the weakness of eBeam? It's speed, right? Well, yeah, wafer market is much bigger than the mask market. That's true. But what eBeam is really good at is doing masks, where the measurement of how fast it runs has an opposite, you know, direction. It's inverse, right? You know, you do wafers per hour on the wafer world, but you measure the amount of time it takes to write a mask in number of hours. You know, the units are reversed. That is the thing that created IMS, and Elmar presented the prototype machine at one of the eBeam Initiative events. I mean, it wasn't the first time it was presented, but he was gracious enough to present it at a forum. So this was really, you know, looking back at it, it was clearly a landmark event, right? And then Newflare also announced their MBM system, and they actually announced their system for the first time in this forum, in eBeam Initiative Forum at SPIAL. And this is often cited picture that talks about how the VSP machine scales in write time based on how many shots you have, but multi-beam writer does not. It's subject to resist and stuff, but not subject to shot count or shape complexity. So that led to another luminary survey. And as I said, one of the important things about what we're trying to do with the eBeam initiative is to help with the collaboration, right? You know, we talked about Moore's Law. I think one of the most impressive things about Moore's Law is not that a human being predicted that, but that it actually is happening, that somehow through collaboration of lots of different competitors and lots of different industries, right? Whether it's chemistry or physics or mechanics or, you know, process equipment or, you know, eBeam or lithography, or there's just like so many different areas, software too, have to combine together and contribute at different times in different ways to keep up with Moore's Law. But somehow it's happening really reliably, if you look at the history, every 2 years, right? And, you know, 2 years isn't enough to develop any new technology, right? You know, it takes like 5, 10 years to do it. So clearly, there's a huge amount of cooperation and collaboration that's happening. And it turns out that there are enough ideas that if one is delayed, others can take over. And in the case of EUV, lots of different ideas had to take over for a while, but eventually it happened. And it happened on time, an amazing thing, right? It's like to be able to predict that is really amazing. But what's more amazing, I think, is that it's happening. And you know, this industry is doing that, right? We're doing that. And part of what we want to do with the eBeam initiative is to help with that collaboration process. Right? It's obviously happening before we existed, but we want to try to help, right? Because we know that we're a group of people who tend to think like that. we like to collaborate, right? And it's really quite remarkable that this happens in the free economy. So anyway, EUV adoption requires multi-beam. This is a survey where in 2017, we asked the people, and then 2018, we asked again. And the number of people who said EUV requires multi-beam mask writing increased from like 75% to 83% total. And as you know, this happened to be right? The luminaries turned out to be right because today, virtually 100% of the fact and also the people would say, yeah, if you're going to write EUV masks, it's going to be written with multi-beam mask writers, right? So that correlation is how the eBeam initiative really participates in the EUV era. At the same time in 2018, though, was this really critical presentation by Franklin Koch. He talked this morning too, but the title of the presentation back then was called Renew, Retire, Replace. And he was talking about how all the attention is on the advanced node, and that's where the money is. We get that. But there is also an important thing to pay attention to in the trailing edge nodes, right? That there's a set of equipment that's 30, 40 years old, right? Older than all the social media companies, right? Companies were not founded before these machines that are still being used in the mask shop were initially installed, right? So he was saying there's a lot of opportunity and a lot of need to service the older technology nodes too. And simultaneously, around this time, the industry, I think, was beginning to realize that there's more than a bifurcation, maybe a trifurcation of the semiconductor business, where not being at the leading edge with EUV was okay to do perfectly good business for IoT devices or some of the automotive devices, right? It was perfectly okay to be 28 or 20 or 14 and be stuck there because you don't have EUV, but you have a perfectly viable semiconductor business that can be profitable, right? And that shift in mentality that you can do that, and also there are companies that are addressing only 193 dry, right? Nodes that can only be done with 193 dry. All of these things are true. And also, of course, the leading edge wafers need masks that are not leading edge, right? The higher layers are not being done with leading edge. So all of those demands combined together should be presenting an opportunity, right? But he said, economically, these older technology nodes have to be addressed with machines that are cheap enough. Can the world figure out how to make a machine that's cheap enough, but still good enough to be able to replace the nodes that were there? That was the question. And he's a luminary of the luminaries, and a presentation that happened 4 years later. This was actually part of a panel session where Mikhail Moslin of Micronic presented this really beautiful looking machine, the SLX series, SLX 1, 2, and 3 combined together. And it turns out, we updated this at the bottom, but 51 machines have sold, of these machines have sold in only like 4 years, right? So clearly Franklin was right in identifying the need in the industry, right? So here again, it's about listening to the luminaries and having opportunities for luminaries to affect what we know. So that's part of what we're trying to do. Now, speaking of that, curvilinear masks is one of the things that we've been working on. we talked about this in 2010 or something, where we didn't have multi-beam machines yet, right? But even with VSB machines using overlapping shots, and together with JOL, we did a study on using overlapping circles and being able to create curvilinear shapes. And the understanding that curvilinear shapes are helpful for process window improvement for wafer, that was really pioneered by luminescent, before this time. But can we write those masks in reasonable time? And much more importantly, can we write those masks reliably so that the variation from mask to mask or shape to shape is under control? That was a key question. And another presentation by Hoya of the study that was jointly done with JOL again talked about how if you do overlapping shots, you can write the shapes more reliably, this is CD uniformity on mask, than if you do it in a conventional way, even if you use the same number of shots, right? Using the same number of VSP shots, you can write the mask with better CD uniformity. So this is another one of those general trends that are important for the eBeam initiative to talk about as kind of a communication medium, right? Of course, what's important in manufacturing, either wafer or mask or anything, any manufacturing, what's important is controlling variation, right? Hitting the nominal, if you're a little bit off, you just bias, no big deal, right? What you gotta do is to control the variation, because if you have random variation, nothing you can do, right? You gotta control the variation. So that's the key thing that we have to pay attention to. And this was one of the things that we've been talking about at the eBeam initiative. And then there was this luminaries, one of the graduates of luminescent, Tom Cecil of Synopsys, gave this really landmark presentation, a great presentation at one of the eBeam initiative events in 2017, where he talked about that. He talked about the control of variation. He talked about the use of curvilinear IoT for 193i. But then, as far as I know, the very first time anywhere, he talked about, curvilinear masks are good for EUV too. Right? Remember, this is back in 2017 when it hasn't happened yet, right? And people were thinking, EUV, who needs IoT? It's just like it's so accurate. You just put down the shape that you want and bias it a little bit, and that's good enough. But he was saying, well, those days are going to be soon over. And when we need more precision out of it, we can get a significant process window improvement by doing IoT for EUV also. And then Micron talked about how there's a significant or nearly 100% improvement in process window, 85% improvement in depth of focus by using curvilinear shapes, particularly for DRAM contact kind of a setting. And that was, 2020 by Ezekiel Russell. So all of these things add up together, and this is a luminary survey again. And it's pretty clear in asking the luminaries year over year that there's a wide understanding by 2020, this is 2020, right? This is a question that was asked in 2020 about what would happen by last year, 2023, right? And majority of the people said, yeah, at least some part of the leading edge masks will be curvilinear, right? 6% not, 94% kind of yes, right? And even with EUV masks, they were saying that only 15% will have no curvilinear component. But it is really quite a shift in a very short period of time, right? You know, that's the kind of thing that we want to try to do with the eBeam initiative, is to communicate these types of trends so that everybody knows that it's happening already, right? And speaking of that, I talked a couple of years ago about how GPUs are great for curvilinear shapes, and OP is what we call it, but pixel-based processing as opposed to edge or contour-based processing in the geometry space. Being pixel-based, GPU is much more the right thing to do. And when you have curvilinear shapes, pixel-based has a lot of advantage. And this is one of the things that I think about Moore's law too. One of the things that helps Moore's law go along is computing, right? Computational lithography, or things that have to do with the mask, or ILT itself, or anything, right? So, but one of the key aspects of Moore's law is that because you can count on the computing that we use to do something is going to advance in the next 2 years also. The problem gets harder, but the computer we're using gets better. So even if you don't do anything to the algorithm, you're keeping up, right? No, you're using something from 2 generations ago, right? 2 nodes ago. But it's all pacing together. So that is a really important part of Moore's law, I think, because computing is an important part of all of this. And being able to count on the computational algorithm that you're using today is still going to be useful when the problem is 4 times bigger 4 years from now, right? That is an important element. But occasionally in every field, like mask making went from 1-to-1 dimensions to 4-to-1 dimensions and created the mask maker's holiday, right? Well, like that. Occasionally, there's a breakthrough thing that happens in what we use. And I think of GPU as that, right? Instead of the CPUs that are continuing to scale like that, right? Mostly by number of threads, but still, scaling like that. GPU is a discontinuity, right? And it's something that if we really take full advantage of it, like TSMC suggested this week, we can really do something great that's beyond just keeping up with the increase in the problem size in the next couple of nodes. And speaking of pixel-based and GPU, something when D2S started doing GPU stuff 12, 14 years ago, but we had no idea deep learning was going to happen back then, Well, but deep learning happened, and deep learning really is an incredible pixel computing machine that can do things that other regular writing code kind of programming has a very difficult time doing, right? And the first to recognize that and present that at one of our eBeam initiative sessions was Yu Xiao of ASML. He was at Brian for a long time, and then he left Brian, and he went to do a bunch of deep learning stuff with social media companies, right? And then he came back to ASML, and guess what he did, right? He bought deep learning and put it together with what he knew about Brian, and put it together. And he came up with 2 different things that he said are very important about the application of deep learning for the IoT problem or OPC problem. And one of them is this slide where he's talking about model prediction can be better, right? You have finite period of time. So even if you can compute something, if it takes like 5 days to do it, it's not useful, right? So being able to use deep learning to do accurate enough prediction of something is an incredibly powerful thing. And Mass 3D, for example, he said, was an area where that can be useful. This is back in 2019 that he said this, right? He also said that the other thing that deep learning is really good at is iterative optimization, initial embedding. So any problem that's solved by iterative optimization, in general NP-complete problems, go through many iterations to come up with an answer. And while you can't replace all of it, because deep learning is a statistical method, you can replace 2/3 of it. You can take the iterative optimization first 2/3 of the steps and replace it with one set of inferencing for deep learning, and then you iterate some more to improve on the solution, right? So these two methods improve accuracy because modeling prediction is better, and improve the speed of execution by taking the initial embedding and just guess the initial embedding answer using deep learning inferencing. Those are the two things that he talked about in this 2019 talk. And sure enough, like everybody doing IoT is doing this now, right? So, yeah, so that's the historical perspective, right? Deep learning is the end of it. It is back in these days, in 2012, 2013, people were talking about who needs more computing power? People were saying, like, I have a laptop, it's good enough, right? I have a iPhone, it's good enough. Like, who needs more computing power, right? Nobody says that anymore, right? And the thing that really happened, I think, is AI, right? Right? Deep learning is such a powerful mechanism, and it's a thing that is what I call useful waste, right? It's basically brute forcing the incredible amounts of computing power, and it's using it in a massive way. Even though it's really wasteful, it produces really useful results, right? So, maybe like 90% of the processing it's doing is not resulting in any useful result at the end. But the rest of the 10% is so good that it's worth the wasting of the 90%. Well, that kind of a method of computing is going to require massive amounts of computing, and ChatGPT requiring 30 racks of GPU-based computers, right? That's I think that's the future of the world, and that's what's going to drive it. So that's the end, but this whole thing, 15 years, we couldn't have done it without you, right? It's in fact all about you. All we're trying to do is enable your voice so that you can benefit from each other's ideas, and we can help with the collaboration. So we borrowed from Hayashi-san's DMP video, and we decided to do a video montage with the role of all the people that participated in panels, that participated in video interviews, that participated and made presentations on the right side. I mentioned Heis Pfeiffer before. There he is, and he's passed away, and I miss him dearly. And then Mike Smaling will come up a little bit later. He also passed away. But yeah, it's an incredible thing to be able to collaborate together with all of you, and that's in fact what's required to make this Moore's Law keep going. So thank you, Jan. Oh, thank you.